So I left off with error. When we're using Taylor polynomials, remember that we're actually approximating the real function. So we have to be able to see, well, how good is our approximation? So what is the error when I start getting close to that? So in order to use approximation intelligently, we need to estimate the size of the error. So your error, just like when you do experiments and calculations in any of your science classes, chemistry, physics, what is it, whatever, your error is the actual amount minus the estimate. So same thing here. Our error is going to be the actual function minus the estimate, which is that Taylor polynomial. You're only interested in the magnitude, so we look at the absolute value of the error. I don't care if it goes over or under, so absolute value. This is also referred to as the remainder. Suppose f and all of its derivatives are continuous. If p sub n of x is the nth Taylor approximation for f of x about a point A, then the error is equal to f minus p, which is less than or equal to m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. That's a mouthful. M is the maximum value of the derivative on the interval between a and xr. So it's the maximum value of the next derivative. The Lagrange error bound is just that difference, that value m. And so sometimes if we change the notation, you'll actually look at both of these here. Your error or remainder is less than or equal to this m over n plus 1. Remember, m is the highest value of the next derivative. So there it is, over n plus 1 factorial, x minus a to the n plus 1, x minus c to the n plus 1. A and c are just constant values of x where this is centered. So the letters are the same, and depending on what, or different, excuse me, depending on what resource you're using, they might use the c, they might use the a. I've seen this notation with an m. I've also seen it with a k. So just know that they're all talking about the same thing. So let's see what happens for us. For f of x equals e to the x, find the fourth degree Taylor polynomial between negative 0.5 and positive 0.5. Find the error when used to calculate f of 0.5. So what are we doing? Well, we want to find the fourth degree Taylor polynomial first. So let's start with our function is e to the x. The first derivative, lucky us, is e to the x. The second derivative is e to the x. The third derivative is e to the x. And the fourth derivative is e to the x. I should use the number 4 there. So fourth degree Taylor polynomial. Now, this expression means that we're centered at 0. Centered at 0. They didn't tell us that we were centered at 0, but if it's between negative 0.5 and positive 0.5, it's symmetric, so we're centered at 0. So at all of these, at x equals 0, these all have a value of 1. All the derivatives are a value of 1. So my Taylor polynomial, I'm going to go fourth degree, is going to be 1 plus, think about this, first derivative is 1, x to the first over 1 factorial, plus 1 x squared over 2 factorial, plus 1 over x cubed over 3 factorial, plus 1 over x to the fourth over 4 factorial. So that is my Taylor polynomial expression, right? So what is the error at 0.5? Well, the error at 0.5 is the actual minus the Taylor polynomial, but I want to know what the error is without actually calculating the error, the original. So you can find the error without calculating the two separately. So this has to be less than or equal to f of n plus 1, the next higher derivative, of x over n plus 1 factorial times x minus c to the n plus 1. That whole expression that's up above. Well, my next highest derivative would be the fifth derivative, which is e to the x, right? So this is going to be So we need to find the value of that m, or that value of that k, or the value of this piece right here. So you want the next highest derivative, the highest value that you could get on the interval that you're looking at. So our fifth derivative is still e to the x. So if we're looking at e to the x, here's e to the x increasing. We want to know what's going on between negative 0.5 and positive 0.5. So here's your negative 0.5 and over here's your positive 0.5. So the greatest magnitude, and again, we're looking for the absolute value, the greatest magnitude is going to happen the furthest to the right over here at 0.5. So the value that goes in, and by the way, these are all 0.5s. This is 0.5, x minus c is where we're centered, which is 0. N is 4 because it's fourth degree. So this is 4 plus 1 factorial, and this is a 4 plus 1. So this would be e to the 0.5 goes in the numerator. In the denominator is 5 factorial. I put my absolute value too soon. And then this is 0.5 minus 0. That's where it's centered at, to the 5th power. And so your error is less than all of that. Okay, so I'm going to pull out my calculator. And I get e to the 0.5 divided by 5 factorial. Let's do it times 0.5 to the 5th divided by 5 factorial. I have that error, which by the way is equal to, we kind of lost a little bit of the notation, the function at 0.5 minus the polynomial, fourth degree polynomial at 0.5 has to be less than or equal to 4.293 times 10 to the negative 4th. Remember that scientific notation, I have an E on my calculator. So this is 0.0004293. Okay, that's the error. I know in your math classes you talk about percent error and things like that, but that is as low as it could possibly be. It won't be any further away than that. So I just wanted to show you what we're actually talking about. What does this really look like? So I've graphed two functions for you. The first one is e to the x. That's the actual function that we're discussing. That's the red one. And then the blue one is the Taylor polynomial. That's the estimate. So obviously, you know, the further you get away from 0, the worse it becomes. That polynomial that we have looks like it's in the parabola family. Well, it's x to the 4th, so that makes sense. Both ends go up. But e to the x is always increasing. So when you're zoomed out pretty far, you're like, it's not really an estimate. But when you zoom in and you're really close, yes, they match up. And so where are we trying to see where they match? Where is that error? We're looking at 0.5. So I'm going to kind of stretch this out here. There's my 0.5. And if you look up here, they're really, really close. That red and that blue line are really close. Now, if I zoom in really extremely here, now they're separate, but start to look at the values on my y-axis. I mean, the tenths are the same, the hundredths are the same, the thousands are the same. So you're talking about the 10,000ths. You're out in 4 decimal places, which makes sense when you look at our answer. It has to be the same value until you get out into that 4th decimal place. And so that's what's happening on your Desmos graph. So I know it's a little bit crazy. I was just sitting here talking to myself saying that this is one of the things that I really struggle with teaching in this class, but I think the picture helps. So that 0.5 is where you're going up and down. I can't select points on this one. Actually, watch this. Let's say x equals 0.5. Try something new. Hey, look at that vertical line. Cooler than a calculator. So at 0.5, and the blue one was the Taylor polynomial, is 1.6484. And on the red one, which was the actual function, it's 1.6487. So if I subtract those two things, 1.6487 minus 1.6484, 3 times 10 to the negative fourth. So I mean, that's how close they are. That's how close the error is. So you want to be able to do that, to find that error without actually calculating the real function or without actually calculating the Taylor polynomial. You want to know how close is that Taylor polynomial. That's the whole point. You want a polynomial instead of that sine, cosine, or e to the x. So kind of crazy, I know. Last example with these. If t sub n is the nth Maclaurin polynomial for f of x equals cosine of x, find the value of n such that that error is less than 10 to the negative fifth. Good grief. Is it spring break yet? So remember that this is 1, 2, 3, 4, 5. There we go. So we want to make sure that we're accurate down to 5 decimal places and below. So we are going to start with cosine. F of x equals cosine of x. We need some derivatives here. The problem is we don't know how many we need, and that's a little bit frustrating because you got to work backwards with these. Third derivative is positive sine of x. Fourth derivative is cosine of x. Fifth derivative is negative sine of x. Okay, and we are centering all of these at 0. Maclaurins, we're headed for 0. So at x equals 0, we've got a 1, 0, negative 1, 0, 1, 0. So how many terms do we need of this polynomial? Well, let's check it out. So my Taylor polynomial, let me switch colors here. My Taylor polynomial is going to be 1, 0 on the first derivative, minus 1 x squared over 2 factorial. The third is skipped, plus 1 x to the fourth over 4 factorial. And by this point, I think you can see the pattern, minus 1 x to the sixth over 6 factorial. So we want to know cosine of 0.2, at what point is that the smallest? So here's where we have to do a little bit of guess and check. So we want this value to be less than or equal to 10 to the negative fifth. So you want that f of n plus 1 of x over n plus 1 factorial times x minus c to the n plus 1 to be less than or equal to 10 to the negative fifth. Okay, so this is, we know x is 0.2. So f to the n plus 1 of 0.2. N plus 1 factorial, we're still trying to figure out. X minus c, well, x is 0.2, c is 0, n plus 1 less than or equal to 10 to the negative fifth. All right, now you basically have to try values for n, which kind of makes these annoying. 0.2 to the n plus 1 less than 10 to the negative fifth. Okay, so let's try some of these. Let's try n equals 1. This isn't going to be it, but let's check it out. So you want the second derivative evaluated at 0.2 over 2 factorial times 0.2 squared. What does that equal to? I'll be right back. So this is equal to negative 0.0199. Definitely not less. And by the way, this is the absolute value of all this. So positive. Not less than 10 to the negative fifth. So let's try again. We need another n value. So this time n equals 2. So this is the third derivative evaluated at 0.2 over 3 factorial times 0.2 to the third. Is that less than 10 to the negative fifth? So I did the third derivative times 0.2 cubed over 3 factorial, and I have 4.654 times 10 to the negative sixth. Because it's to the negative sixth power, that is less than that 10 to the negative fifth power. So we did it. Good job.